All right, let's do this. Where we stopped last time is somewhere around here, I believe. So we are using some data to calculate and predict housing prices using machine learning. And I'm following a book named Hands-on Machine Learning using Scikit, Keras, TensorFlow, if I'm not mistaken. So here I'm using the head method, which is found, I think, in the pandas data frame library. Yeah, it is. So this method is used to display the first few rows of the data frame. And by default, it shows 5 rows, but okay, we can specify different number of rows as an argument. That's it. We have data, we have how many? 10? I think we have 10 attributes, and each row represents one district. So yeah, that's it. Doesn't do anything. We just quickly inspect the first few rows of our data sets, and we use it just to check if the data is correct. Now, housing info is another method that we are using, and it's useful to get, let's say, a quick description of the data. So we get the total number of rows, each attribute's type, and the number of non-null values. So supposedly we should have 20,640 instances in the dataset, and this attribute here has only 20,433 non-null values. So how many districts? 207 districts are missing this feature. So most probably we'll need to handle this at a later time. So all of these values are numerical except the ocean proximity, whose type is object. So it could hold any kind of Python object. But since we loaded this from a CSV file, we know that this must be text property. And here we can look at some of the values of the ocean proximity attribute, and we can see that actually the attributes itself are repetitive, so most probably they are categorical in nature, so we can categorize these values. That's it. Now, this method is used to display the categories and how many different districts belong to each category, and we can do this by using the value counts. Yeah, so basically the value counts is used to count the number of occurrences of unique values in a column, and it returns a series sorted by the most frequent values first. So it says here that less than 1 hour ocean appears this many times, inland appeared this many times, near ocean, near bay, and no, this is inland and this is island. All right. We could most probably also normalize this. We could see the percentages instead of row counts, but for now, I don't think we need this. So let's continue. Now, describe. The describe method shows a summary of the numerical attributes. So we have count. It's mostly self-explanatory. And by the way, it only shows the values of numerical attributes. So if I'm not mistaken, also ocean proximity is missing from the list of attributes. But okay, let's do this. So we have count, we have mean, we have max. I mean, these rows are more or less self-explanatory. The count is the number of non-null values. The mean is the average value. STD is the standard deviation. This is the minimum value. This is the maximum value. What else? Oh, yeah, we have the median and the quartile. Basically, 25% of values are below this value. 50% are below this. 75 are below this. So let me just maybe take a column and explain it. Okay, maybe the age of the house. So okay, we have 20,640 values. The average value is 28.6364. So the average age of a house is 28 years, around 28 years. The minimum value is 1, which, okay, it is probably a new house. The maximum value is 52. Now here we have the quartiles. So 25%, 1/4 of values is below this value. So out of the 20,640, 25% of those are below this. So they are from 1 to 80. 50% are below this, and 75% are below this value. Standard deviation, how dispersed the values are. So, yeah. I was stuck trying to explain the standard deviation. Basically, it's how spread out the values in a dataset are. And if we have a smaller STD, datasets are closer to the mean. If we have a large STD, data's points are more spread out, so there's more variation. There's a method that calculates this, but most probably I won't bother myself with this right now. Okay. Next thing, the following cell is not shown in the book. It creates the project folder. Okay. Okay, so what this is used to save figures or IT. Now we can also plot histograms. This is just some configuration for the fonts. Now this is important. So we have housing, histogram, we have the amount of bins, the fig size. So yeah, basically what hits this is a method in pandas which creates a histogram in order to visualize the distribution of numerical data. These parameters here, bins and fig size, customize how the histogram is displayed. Bins defines the number of bars in the histogram, and fig size sets the figure size to 12 inches wide and 8 inches tall for better visibility. So what I assume here we must have 50 bins, yeah, and we can see it best here, housing median age histogram, in which we can see 50 separate bins for each level of detail. All right, so what can we see here? So we have the median income attribute, and the way it's displayed seems like it's not expressed in US dollars. So a description of this says, so we checked with the team that collected the data, and we are told that the data has been scaled and kept at 15 for higher median incomes and at 0.5 for lower median incomes. And the numbers represent roughly tens of thousands of dollars. So the 5 would represent $50,000. This would represent 100. Someone is earning a lot of money here. So these are pre-processed, it seems. All right. Housing median age and the median house value. For some reason they are capped, as you can see by this bin right here. Basically what means being capped, it means limiting the values, at least in the histogram, limiting it at a certain value. All right, let's create a test set. So why do we do this? It's going to be a test set. So basically, just what we need is to create a test set, and theoretically speaking, creating a test set should be simple. We need to pick random instances around 20% of the dataset, and we need to set them aside. Test set is basically a subset of the data set that's used to evaluate the final performance of a trained machine learning model. And it should consist of data that the model has never seen before, which will help to measure how well it generalizes to new unseen data. So we have a method here. So this method, a shuffle and split data. Oops, I forgot, sorry. Let me turn off my tablet. So what do we have here? We have this method, shuffle and split data, which performs random shuffling and splitting of data sent into training and test sets. So let's break this. So these are the function parameters. I assume this would be the data set. The test ratio should be the proportion of the data to be allocated to the test set. Next thing, we shuffle the indices. Here we are creating a random. Let me just maybe increase the size of it. Yeah, here we are creating a random permutation of data of indices ranging from 0 to basically from 0 to the length of data. Basically, this ensures that the data is split randomly without creating any bias. So this is the size of the set. Here we are just multiplying the total number of rows by the test ratio to get the number of rows for the test set. And we are using the int, we are casting it to int in order to ensure that we have a whole number here. All right. Here we are grabbing the shuffled data and we take the first this many indices from the shuffled list. And this will take the rest of it. These two lines of code basically. So it's like from 0 to here. And this is from here to end. And yeah, we are just returning the data. We use this to make sure that we randomly split the data, to make sure that there's no bias when selecting training and test sets. And we are using this specifically in order because we need separate training and test data. All right, here, so the length of the training set is 16,512. This should be the rest of it. I assume if we would sum these two numbers, we would get this number. And here it says to ensure that this notebook outputs remain the same every time we run it, we need to set the random seed. Yeah, okay, this happens because if we run the program again, it will generate a different test set. So what we need to do is to have the outputs remain the same, and for that we need to set a random number generator seed before calling the permutation. So it always generates the same shuffled indices. So the biggest problem is here how to change the test set. Why actually to change the test set on every run? Because the method that does the random permutation generates different random shuffles on each run. The test set will be different each time you run the program. So what we need to do is to save the test set for future runs. And when running for the first time, we need to save the test set to a file. And on future runs, we need to load the test set instead of generating a new one. So what we could do is compute a hash of each instance identifier and put that instance in the test set. If the hash is lower than or equal to 20% of the maximum hash value. And the test set, this will ensure that the test set will remain consistent across multiple runs. All right, so this piece of code will split a data set into training and test sets deterministically. Basically, it will always have the same split as we mentioned before, and it will use unique IDs. And unlike random shuffling, this method ensures stability even when new data is added. So what are we doing? from zlib, we are importing crc32, which is a function from the zlib module that generates a 32-bit hash for a given number or string. And we will use this function to assign instances to the test set deterministically. So this method isID in test set will determine whether a given instance ID should go into the test set, and it will convert an identifier into a 64-bit integer. Where is it? Here. And it will compute the CRC hash of it, and it will compare this value against test ratio times 2/32. And if smaller, the instance will go into the test set. If larger, stays in the training set. And I have no idea why. I had no idea why this was happening. So why are we using this number specifically? Because CRC32 produces values in the range from 0 to 2 squared by 32 minus 1. So test ratio multiplied by this value will ensure that the probability of being in the test set matches the test ratio. So if the test ratio is 0.2, then 0.2 times 2/32 is a really huge number. It's not angles. I want. All right. How much is this? So it's a pretty huge number. And all IDs with a hash below this number will go into the test set. And the rest will stay in the training set. And now this method, split data with ID hash, will split the data frame into train and test sets based on a hashed ID. And will extract unique IDs from the dataset. Where is it? Data ID column. It's here. It will apply the method that we talked about to each ID to decide if it belongs to the test set. It will use the lock filtering. And it's really good because it avoids the randomness problem. The IDs determine whether data is in the train or test set. It's great for evolving data sets, and it already uses a hashing algorithm, CRC32. So let's say we have an example of this. No, I don't want to move you. I want to move you here. All right, let's do an example. So we have a small data set. Let's say these are the maybe let's use a different color. These are the IDs. These are the features, and the ID can be 1, 2, 3, 4, and 5, and the feature can be, I don't know, 3.2, 5.1, 6.7, 2.9. So we want to split this into 40% or 60%. We can use 40% instances in the test set and 60% in the train set. So we need first to check the each ID. So basically what this function does, the CRC identifier, CRC32 ID, of course we are also converting it to int64, but in this case, so we get a hash and I don't know, some values will go into the test set and some will go into the training set. And the lock is just filtering rows based on conditions. So data lock in test set will select rows where in test set is set to true, and the one with lambda will select where in test set is set to false. And if we print this out, we would have 3 instances in the train set and 2 in the test set. I don't know why is this moving. So CRC32 will compute a hash of each ID. And so I think the housing dataset doesn't have an identifier column. So the simplest solution is to use the row index as the ID. So this is the data that we get, and this is the index column. All right. So as I said, we prepare the dataset for splitting by ensuring that each instance has a unique identifier, and then we split it into train and test set deterministically, which means without randomness. With the first line here, we are using the reset index method, which adds an identifier and it resets the index of the data frame. And the old index will become a new column named index. If we don't have it, so if I do housing head, let me execute all the cells above. And if I execute this one, okay. So I had to print out the train set and the test set. I didn't know this. So the new index column will act as a unique identifier for each row. And here in the second line, we actually split the data. We call this method split data with ID hash, which we defined here, which actually splits our data set deterministically, as I said, every time in the same on the same elements. So how I actually learned this is I don't mess a lot with the code. I don't remember the code. I remember the concepts, and I'm gonna use the concepts in the future. So what we do, we hash the index and we decide whether it belongs in the test set or the train set based on the test ratio. Where is this method? There is this method that uses the hashing algorithm. I think it's this one. So based on the index, we determine the test set membership. So let's actually print this. Maybe it's gonna be easier to print CRC32 0. So bytes like object is required, not int. Why not int? Let me remove this. So this is the identifier. Okay. I need to convert it to int 64. So now, if I do print CRC32 numpy 64 0, what am I gonna get? Why am I having I can remove it from here. And here, if I print, why am I still getting the same output is truncated? Yeah, what? Why am I? Do I need to save this? I did save. Okay, now if I run everything above, and if I run this guy again, okay, so this is the result. And I think it's always the same. Yeah. If I print 1, and if I print 2, super percenter, and if I print 3, all right. So basically this will always provide the same results. Will provide the same results in different environment, is the question. I think it will. It should do that, right? Yeah, I did some Googling and it says, yeah, CRC32 will always produce the same result for the same input because it's a deterministic hashing function. All right. Maybe I should write this. Oops. CRC32 always all right, so CRC32 always provides the same result because it is a deterministic hashing algorithm. All right, so we have a new index. The new index is a unique identifier. So there is a warning about using the row index as a unique identifier when splitting data into training and test sets. Why? So if you use row index as an ID, new rows must always be added to the end, and rows must never be deleted or reordered. Otherwise, your train test split will change, and the same instances might switch between train and test sets, which is bad. All right, so an example of this could be if we have an original dataset, and if we have, let's say, print train set head. All right, if we have this dataset, why isn't it in one line? What if I? No. All right, for some reason, it's in multiple lines. So I have this. If I would remove, where's my second index here? Okay, if I remove something, and this is my original data set, and if I delete, let's say, this row, the second row, and our row indices will shift after deletion, the train and test split will change, and the sample that was originally in test set might now be in the training set. It's bad. It leaks information. It causes data contamination. So what we need to find the most stable features to build a unique identifier. And here it says, districts, latitude and longitude are guaranteed to be stable for a few million years. So you could combine it into an ID like so. So this is what I assume is the ID. Housing with ID is housing longitude times 1000 plus housing latitude. How do I know this? How do I know this is unique? Also, have I run this? What if I run this again? Why is my ID not changing? Housing with ID. It's housing. Train set. So, okay, I understand. Latitude and longitude would always remain the same. And I can use latitude and longitude to create a stable ID like this, like we just did. All right. But yeah, this happens because latitude and longitude together create a unique identifier for each district. And the same location will always generate the same ID, which ensures a stable split. Here is the ID. So this is the ID, and this is the index. So instead of using the row index, we can use ID as the unique identifier here. How do I know this is unique? That's my question. How do I know this is unique? Maybe I can check how many unique variations exist. How can I do this? Okay. So I have housing. I'm getting the ID. I'm getting value counts, which is gonna print. It's because it's housing with ID. It's not housing, right? Will work now, yeah. So I have value counts. So I have value counts, and then housing value counts greater than 1. It's because it's not housing, it's housing with ID. Yeah, I knew that I had fucking duplicates for some reason. Why? All right, let's trust the book. Let's trust the book that the book knows what it's doing, because there's definitely some duplicates here. Okay, scikit-learn provides a few functions to split datasets into multiple subsets in various ways. So the simplest function is train test split, which is here, which does what? So this method will randomly split the housing dataset into training and test sets, and it's using the scikit's train test split function, which is this guy here. So how it's work? How does it work? Same thing. This is the full dataset to split. I want 20% of data to be assigned to the test set. What's the random state doing? Ensures the split is reproducible. Okay. If we run, okay. So I think I understood. The solutions above were custom solutions, something that we could, write ourselves by hand. But this is actually something that's provided by scikit-learn. Let me just write this. I think this is something that I should know, and something that's important. Test split. This is the data set. All right, as we said, so this is the random seed. So the book says, so far we have considered purely random sampling methods. This is fine if our dataset is large enough, but if it's not, you run the risk of introducing a significant sampling bias. All right, so when someone at a survey company decides to call 1,000 people, so when they want to call 1,000 people, it's not only 1,000 random people, it's 1,000 people that are representative of the whole populations with regard to the questions they want to ask. So if the population of females is 52% and the population of males is 48%, so they will try to keep this ratio, this gender ratio, during the survey, and this is called stratified sampling. So stratified sampling, in which the population is divided into homogeneous subgroups called strata. So this guarantees that the test is representative of the overall population. All right, let's turn this off and let's keep going. So if we have 5 housing prices, like 100K, 150, 200, 250, and let's say 300,000. So what is the middle value? It's 200,000, because that is the middle value that's found in the middle of the data set. But if we add another value, let's say a pretty high value, let's add 10 million. So the average of this would be around 2.1, 2 million and 180,000, which is a not good representation of the actual house prices. Sorry if we remove this value, but the median is still $200,000, which represents the data better. So the median income is a key factor in predicting house price. We need to make sure that income categories are evenly distributed, because the median income is supported, right? We need to split the data carefully. We need to split the data in a way so that the training set needs to have a more distributable median income values, and not make the model biased or unreliable. So we need to create something called income categories. Because median income is continuous, we can convert it into groups or categories, or another way to say this is buckets. So we can group, I don't know, low income into a certain group, middle income into another group, high income and very high income. And then we stratify the split, and we make sure that each income category is well represented in the training set and the test set as well. Actually, take a look at the median income here. And you see that most median income values are clustered around here somewhere in this part of the histogram. But you know, there are some incomes that go all the way to the right. And it's important to have a good number. Oops, I forgot to this is the median income graph. You need to have a sufficient number of instances in your dataset for each division, for each stratum. Or else the estimate will be biased. So what we need to do is create an income category. And where is